we're going to go ahead and get started. People trickle in late, they do. I got most of your money's points. If you turned them in just a few minutes ago, then I haven't looked at them, sorry. But if you turned them in reasonably early this morning or yesterday, I looked at them. So here's the plan. I'm going to go over the topics that kind of came up the most from you guys, and then just open floor for questions and stuff after that. This review, so if I didn't touch on something that you're not clear on, we can obviously talk about that as well. I posted a review sheet in, I guess, the week 14 folder. So that's a list of topics, essentially, kind of broken out by how we looked at things, and if you know the answer, or roughly know the answer, or know how to find the answer to the things on that, you're probably going to be fine. Those are the big points that I wanted you to pick up this semester. So, we'll go through that, but I think we're just going to start. I'm going to skip around a little bit just based on how you guys ask questions, but yeah, feel free to stop me at any point. But we're going to just start basically back with types of epidemics, or technically there's types of epidemics means different things that can be considered epidemics. But what I think the person that wrote that was asking was actually the difference between endemic, epidemic, and pandemic. Am I probably correct in assuming that's what, I don't remember who asked it, I didn't write down who asked what, I just wrote a list of everything. But who can tell me what the difference between epidemic, endemic, and pandemic are? What are those three things? Anyone but you, because you answer all the time. I know you know the answer. Well, yeah, you kind of count. These two people right here are always answering the questions I want the rest of you guys to think. So big bonus points for you. I'm pulling out of the rest of the class. Yeah.
Epidemic is a disease in a defined population over a period of time, or the expected level of disease, or an increase.
Can you say that louder?
Yeah, an increase above expected level of disease in defined population over a time period. Endemic is persistent or expected level of disease, it's like the base rate. And pandemic is widespread epidemic over a large area geographically.
Exactly. So, an epidemic is anything that exceeds the endemic rate, right? Because the endemic rate is the expected rate of disease in a population. So there are some things like the endemic rate for, I don't know, Ebola in the United States is 0. We do not expect to see Ebola in the United States. So over that area and over any particular amount of time, if we even saw one case of Ebola, we could consider that an epidemic because it's significantly out of the norm for the United States. Now, if we look at the flu, the endemic rate of flu from October through February or whatever, during what's classified as flu season, there's going to be a base rate of flu. I'm actually not sure what it is, but there's a base rate of flu, and that's the endemic rate. And we consider it an epidemic if the number of people that get sick substantially exceeds what we would expect to see at the baseline. Where do you think we get the information for the endemic rate? Yeah.
With hospital records?
It could be hospital records, depends on what it is. It could be like the baseline survey data that we do. It could be, so for flu, seasonal flu, yeah, it's probably, I think, usually like doctor and hospital records. Physician reporting, stuff like that. But so we have an idea of what the base rate, what the expected rate would be, and we get that information from the year prior, right? So we can look over time and see, yes, we usually have 10 cases per 1,000 people over a 2-week period or something. I'm making those numbers completely up. But anything that falls outside of that, anything that exceeds that, we consider an epidemic. Now, as an epidemiologist, epidemic and outbreak are the same thing. In kind of the lay press and the way that the general population thinks about it, they usually think about an outbreak as this tiny cluster and an epidemic as being a little bit bigger. But as far as technically speaking, the two terms are synonymous. A pandemic is simply a widespread epidemic, usually spanning multiple countries or worldwide. right? That's the only difference there. So it's obviously above the base endemic rate that we would expect to see, but it's just spread over a larger region. All right, any questions about endemic versus epidemic versus pandemic? Okay. So now we're going to talk about screening tests. So screening, I think we covered week 2 or 3, way back at the beginning of the semester. There's a couple of points we're going to make. So first we want to talk about the characteristics that make a disease a good candidate for a screening test. Right? So not every disease is a good candidate for a screening test. But certain diseases that have certain characteristics are. Anybody tell me at least one of the characteristics?
High prevalence.
A high prevalence in the population, right? Why would that be important?
Because then it affects the accuracy, the sensitivity versus like
Positive predictive value,
Yeah.
I guess. Yes, but it also, even on a larger level, so yes, it does affect the positive predictive value. On a grander, I don't know, what theoretical scale, if it's not a big problem, so if there's not a high prevalence of it, and it's not making a big public health impact, maybe we don't care as much. Not that we don't care about these people that are getting sick, but that may not be where we want to spend our limited funds. So we want it to have a high prevalence in the population of interest. What else is a characteristic of the disease? Yeah.
You have to be able to do something about the disease once you find it.
Yes, there should be a treatment available because it really doesn't do you a whole lot of good to be like, yeah, you're sick. Sorry. Now you know. Now you can worry about it. Because when do we do screening? What is the purpose of a screening test?
Just to identify whether or not you have this.
In what type of person, though?
Asymptomatic.
Asymptomatic. People that do not know they're sick. So it's to identify the presence of a disease or to assess if people probably have the disease and people that would not otherwise know they were sick. Which leads me to the next point of a characteristic of a disease.
It has to have a long latency period.
It has to have a long latent period. It has to have a long pre-symptomatic period. So the time between when someone is biologically sick and when someone actually notices that they're sick. We would expect that period to be a wide window. Because if it's only a day or two, we're probably not going to screen people and find them. They'll just get sick and then go get treatment. So we want it to be a big public health problem, so high prevalence. We want it to have a long pre-symptomatic period, long asymptomatic period before people get sick. I just forgot the last one that we were talking about.
Treatment.
Yeah, so treatment available. And let's see, and the treatment, so we want the treatment to be available, but we also want the treatment to be, we want you to be able to receive the treatment in this pre-symptomatic period. So the whole point is that we should be able to identify people early and treat them early to either keep them from getting sick or to keep it from getting worse, right? So we want to identify people that are HIV positive before they develop AIDS, so we can treat the HIV and hopefully prevent them from developing AIDS, right? All right, so those are the characteristics of a disease that make it a good candidate for creating a screening test. What are the characteristics of a good test?
Inexpensive?
We would want it to be inexpensive, yes. That in and of itself is not, but at a large scale, then absolutely yes. We want it to be inexpensive and hopefully easy to administer, right? Because we're going to be using it over a large group of people.
We want it to be as accurate as possible.
Yes, we want it to be as accurate as possible. So we want it to be sensitive and specific. And more broadly, we can say we want it to be a valid test. When we say it's a valid test, it means the test is actually identifying what we think it should be identifying. So if we have a test, a screening test for diabetes, we want to make sure that it's picking up people with diabetes, right? That's a valid test. On that same vein, we want it to be a valid test, but we also want it to be what?
Reliable?
A reliable test. Who wants to guess what reliable means? We shouldn't be guessing, we should guess. Yeah.
Accurate or consistently accurate.
Consistent. Yes. So a test can be reliable and not actually be accurate, right? You can very reliably and consistently measure the wrong thing. But we want to test, you can't have a test that's valid unless it's reliable. So it has to, over time, each time you give people, the same person a test, you should get the same answer. It should be reliable.
Would you say like reliable synonymous with precise, so like precise and accurate?
No. Precision is different. So reliability refers to the ability, it's, for all intents and purposes in this class, it's consistency. So the ability to get the same answer every time. Precision is really talking about, when we talk about precision, we're really talking about more statistical precision and the ability to like accurately, narrowly identify like the number of people that have the disease. So, well, precision is a different concept that doesn't necessarily apply to reliability and validity, except for your ability to accurately estimate the validity. So you can come. So when we talk about sensitivity and specificity, we come up with an estimate of sensitivity, right? So we do our 2x2 table and we calculate the sensitivity. Precision refers to how closely that that estimate we have, within what window we're probably getting the right answer. And that is beyond the scope of what you guys need to know. You need to know that reliability is talking about being able to get the same answer every time that you get the test, and validity is talking about getting the right answer when you administer the test. All right, so this leads us to talking about sensitivity and specificity. So when we're talking about sensitivity and specificity, we always, well, not just that, pretty much everything that we do in this class, we start with a 2x2 table. We do different things with that, but we're always talking in 2x2 tables. Because epidemiologists like to put things in categories. Stuff them in boxes. All right, so we have a 2x2 table. When we're looking at sensitivity and specificity, in order to estimate those, we have our screening test, and then we also have to have something that we're comparing it to. So we usually call this our gold standard. The gold standard test is the true answer, supposedly, right? Our gold standard is telling us what the truth is, and then using that gold standard, we can then compare the results of our screening test to see if we're actually getting at the truth when we use our screening test. So, let's say that we have, I've got an example here. Let's say we have a new tool that we've developed to screen people for colon cancer. So typically colon cancer screening what would you think the gold standard for identifying colon cancer would be? A colonoscopy, right? Well, everyone knows that colonoscopies are no one's favorite activity. It's not an enjoyable procedure for people to have. So people are told that they need to get it every 5 years, I think, once they turn 45 or 50, something like that. They keep changing the regulation or the recommendations. But so people are supposed to regularly get a colonoscopy. Well, but you, in your ultimate brilliance, have come up with this new screening test that you're hoping will be able to identify people that have colon cancer, and people won't have to get a colonoscopy anymore. So it's a less invasive test. People will think it's better. They're more likely to do it. So we want to see if our new test that we've developed is going to validly and reliably assess or identify people with colon cancer. So our gold standard in this case, we're going to conduct a study. Whenever you're looking at these measurement components, you conduct a study to look at them. So you give people your new screening test, and you give those same people a colonoscopy. So your gold standard is going to go on the top. So people that test positive with the gold standard, and people that test negative with the gold standard. Then our rows, we're going to have the results of our screening test. People that are positive based on our screening test, and people that are negative based on our screening tests. Right? So, when we're looking at this table, which cell is referring, so I'm going to go ahead and label them right now. So we'll label this one A, this one B, this one C, and this one D. Okay? which cell refers to the people that are true positives according to our screening test? A, right? A true positive is someone our screening test identified that as positive that really does have the disease based on our gold standard. What about a false positive? B. So remember, these are the screening tests. So these are all the people that tested positive. The top row are the people that tested positive on our screening test. So people in B had a positive screening test, but they don't really have colon cancer. So what about the true negatives? Who are the true negatives? D, right? They tested negative with our test. They tested negative with the gold standard. And so the false negatives are C, obviously. They really are sick, but our screening test didn't identify them. All right? So we have true positive, the false positive. Oh, sorry. False negative and true negative. Okay. So everyone should be able to clearly identify which cell is which, right? You guys all understand why they are the way they are. Okay, excellent. So let's say we conducted our study. And we got these results. We found 679 individuals that screened positive with our test, that according to the gold standard were positive for colon cancer. We had 21 people that screened negative, but that our gold standard, the colonoscopy, said did have colon cancer. We had 93 people who screened positive, but aren't really sick. And we had 9,207 people who screened negative and really are not sick. Alright, so we have this data, but now we have to use this data somehow to identify how well our test is working. So, who remembers what sensitivity refers to?
Eliminating false negatives.
I'm sorry?
Sensitivity is eliminating false negatives.
Kind of, but that's not entirely right. You're close. Don't think in terms of negatives, think in terms of positives. Sensitivity is referring to how well your test is identifying the people that are positive. Okay? So it's the proportion of people that tested positive out of everybody that is sick. So sensitivity is how well your test is actually identifying the people that are sick. So remember, we all remember what proportions are, right? So it's the proportion of people who tested positive that really, out of everybody that truly is sick. So we calculate our sensitivity. As 679, the number of people that are true positives, over the true positives, plus the false negatives. False positives. Oh, did. True positives over true positives plus false positives, sorry. Oh my gosh. I should not talk anymore. I have ruined you all for this entire exam, and when you miss this question, it's going to be true positives over true positives plus, what are these? Because I've lost my mind. Anyway, when we're talking about sensitivity and specificity, you're talking about this number over the column total. Let's talk about that. Let's talk about it. A over A plus C. Talk about that one too. Anyway, so we get a sensitivity, and this is because I did the math already, of 0.97. This is pretty good, right? So 97% of the time, 97% of the people that are Sick, we're classifying them as sick. Doing a good job. Our test is pretty sensitive. Now, specificity is talking about correctly identifying the people that don't have the disease. So that's saying, how well are we picking up these people? How well are we saying the people that aren't sick really aren't sick? So when we're talking about specificity, we're talking about the number of people who truly do not have the disease, or the number of people who tested as not having the disease out of everyone who truly does not have the disease. So it's the proportion of people that test negative out of everyone that's not sick. So we have a specificity, 9207 divided by 207 plus 93. So our specificity here is 0.99. So we're doing a really, really super good job of saying the people that aren't sick really aren't sick. So sensitivity, we're picking up the people that are sick. Specificity, we're making sure that we're eliminating the people that are not sick. All right. Sensitivity and specificity are characteristics of the screening test. It does not matter what the prevalence of the disease is in the population. Sensitivity and specificity are characteristics of the test. Epidemiologists like sensitivity and specificity. It tells us something about the measure. It tells us how well the measure actually is identifying the right people and eliminating the people that shouldn't be classified as having disease. Positive predictive value is more clinically relevant. Positive predictive value, now we're talking about ROPES. So positive predictive value is the number of true positive, number of people that truly have the disease that tested positive out of everyone that tested positive. So now we're saying, what's the probability of you actually having the disease, given that we know you tested positive? So we're kind of looking at the reverse thing. So now we're starting with people that test positive, and it's like, okay, you had a positive test. What's the probability that you actually have colon cancer? That's what positive predictive value is telling us. And positive predictive value is dependent upon the prevalence in the population. So if you have a very low prevalence in the population that's screening, doesn't matter if you have a really sensitive and specific test, you're going to have a lot of false positives. And false positives are not great, because then you have a bunch of people that are getting extra tests and have all that emotional baggage that comes with being told that you're sick when you're not. So let's walk through a positive and negative predictive value, or just a positive predictive value example. So when we're talking about positive predictive value for this test, it's the proportion of people that truly have the disease that tested positive out of everyone that tested positive. So now, our PPV, we're talking about 679 over 679 plus 93. So for this one, we get a positive predictive value of 0.87. That's a pretty good positive predictive value. So 87% of the time when that test screens you and tells you that you're sick, you really are sick. So we don't have a huge number of false positives in this particular instance. Who remembers how to calculate the prevalence? So let's find out what the prevalence is in this population.
Choose the calculate the total number and then get the actual 679 divided by the total of the full boxes.
Well, it's actually going to be 679 plus 21. So it's everyone that's truly sick out of everyone in the population, right?
7%.
Yeah, so it's 7%. So the prevalence in this population is 7%. Alright. So now let's say, which generally speaking they say if you're doing a screening test you want the prevalence to be in the population to be around 10%. So we're getting close, right? Which is probably why we got a positive predictive value of 0.87. So let's say, yeah, sorry.
So isn't there usually a trade-off between, you said, sensitivity and
There is a
specificity?
trade-off between sensitivity and specificity.
And how are they both so high in this case?
They can both be high, but you're never going to get a sensitivity of 0.99 and a specificity of 0.99. It's not going to happen. And what I didn't do any examples like that. What generally happens as you increase the sensitivity, not generally, always happens, as you increase the sensitivity, the specificity drops, and vice versa. But most of the time, tests that are used are more specific than they are sensitive. Now, you want a highly sensitive test, but a lot of times specificity is equally as important. So let's say, okay, so we know that the prevalence in this population is 7%. I'm going to change the number so now we'll have a prevalence of 2%. Alright, so now we have a prevalence of 2%. Go ahead and calculate the sensitivity. What's sensitivity again? This one over this plus this, right? What's sensitivity? 0.97, exactly the same as it was before. So our test, the sensitivity of the test hasn't changed. What's the specificity of the test? 0.99, it's the same. Sensitivity and specificity have not changed. What has changed is the prevalence. Now calculate the positive predictive value. So remember, positive predictive value is the proportion of people that truly have the disease out of everybody that tested positive. .66. So even if we're using the same test, and the same test has the same accuracy, if you apply it in a population with a low prevalence, you're going to get a worse positive predictive value. Now what does it mean if we have a positive predictive value of 0.66?
People who test positive, 66% of them have it.
Yes. So out of everyone that's testing positive, only 66% of those people are actually sick. Which means that
Not a very accurate test.
it's still an accurate test. So the accuracy of the test, sensitivity and specificity, has not changed.
It's not helpful. So like, the test isn't helpful.
Yeah, so now what's happening is that there are a lot of people that think they have colon cancer and go in for a whole bunch of extra testing, because then they'll probably have a colonoscopy and have other things, only to find out they didn't have colon cancer. So now you have 34% of people that were screened with this test have gone on and gotten all of these that tested positive, have now had to go get all this extra testing, which spent a lot of extra money and a lot of emotional trauma. There's a whole line of research about how bad it is to be told you're sick when you're not. Imagine that's probably not good for you, for your mental health. Right, so what we need to make sure, which is why the characteristics of the screening test and the characteristics of the disease are so important when we're talking about screening tests, because you want a sensitive and specific test. You want a good screening test. But you want to apply it in the right place. So that when you're applying it in a population with a high prevalence, you know that you're not creating all these false positives and all this extra work. Right. Does everyone at least get the gist of the difference between sensitivity, specificity, and positive predictive value? Are we good on these concepts? Excellent. All right. So, I hate chalk. I don't have marker boards in here. Where's mine? So let's talk a little bit about the different study designs. You know what? Let's back up. So we've talked about the prevalence here. What is the difference between incidence and prevalence? What is incidence?
The new cases that appear within the population.
The number of new cases of disease. So incidence itself, just an incident case is a new case. A prevalent case is an existing case. When we talk about incidence, we're either talking about cumulative incidence or we're talking about incidence rate, right? Cumulative incidence means we have an identified number of people over a certain period of time. No one's moving in and out. We have a static population. So we know the absolute number of new cases within a specified number of people over a specified time. Incident rate happens when we have, sorry, did I say dynamic? I meant fixed. Incidence rate is when we have a dynamic population. So we have people moving in and out of the population. So we can't get an accurate, complete head count, but we can look at the amount of person time so that we can estimate the amount of time each person contributes to this group that we're counting. And so incidence rate is simply the number of new cases over the amount of person time. Both of them, incidence rate and cumulative incidence, we're talking about new cases in a specific group over a specific period of time. It's just that the denominator is different depending on how you can count your population. So if you have a total accurate count of your population, you're talking about cumulative incidence, or that you can calculate cumulative incidence. If you don't have a total accurate count of your population and you're counting people as person time, so the amount of time they're contributing to your population of interest, then we're talking about incidence rate. But both of those are referring to new cases of disease. Prevalence is not a rate. Prevalence has nothing to do, it does not have time in the denominator. So we can talk about point prevalence or we can talk about period prevalence. But we're not talking about, so in incidence we're talking about new cases over time, right? Over a specified time period. And prevalence we're saying today, on December, what is it, 4th, something like that? 5th, no idea. On December 5th, what is the prevalence of diabetes? Sometimes we say, in the year 2012, what is the prevalence of diabetes? That counts anyone that had diabetes in 2012. And so we would call that a period prevalence, but it's not a rate. We're not counting people over time. But prevalence is existing cases of disease. Right? So we're good with that distinction? All right. Lost my place. We got incidence, we got prevalence. What was I talking about before that? I'm sorry?
You were going to go for study design.
Study design, thank you. All right. Very important. We're talking about study designs. We get different estimates based on different study designs. So, the main designs that we talked basically about observational designs, and then we talked about experimental designs. We spent a whole lot more time on observational designs because that's kind of the fundamentals of epidemiology. What is the difference? What makes something an experimental design? What are the necessary features for something to be experimental? Yeah.
You intervene on a variable.
Yes. So there's in research or investigator intervention. So you manipulate something, and so you told me the one that everybody forgets.
Randomization to groups.
Randomization of treatment groups. That's right. Excellent. So, in order to call something an experimental design, you must randomly assign people to treatment groups, and you as the investigator have to manipulate the independent variable. So, that means you're applying a treatment. You're applying an intervention. Right? But you are in control. You are the puppet master when we're talking about experimental intervention. In observational research, you don't do anything. You are observing what has happened or what is going to happen. So people exist in naturally occurring groups, and then you watch what happens, but you as the investigator don't manipulate anything. What are the main observational study designs that we talked about? I need to spread you guys around the room so at least I look somewhere else other than. What are the main? Sorry. Yeah.
Case study moving forward, or observational.
So not a case study, a case control study. There you go. Because a case study is very different. A case study, if any of you guys decide to go to medical school, they're more common for physicians because a case study is simply saying, I have this one really interesting person and I'm going to talk about them. Or you can have a case series where you have 5 interesting people and you talk about those 5 people. But a case study is really just one person, so it's technically not really a study at all. Case control study is the foundation of epidemiology, essentially. Now, so we have a case control study, what else? Someone in that back corner. Okay, that works. Cohort study, right? And we can break cohort studies up into what kinds? Retrospective and prospective. That's right. What else did we talk about?
Cross-section.
Cross-sectional study designs. So cross-sectional study designs, everything occurs at one point in time. We're going to elaborate on all of these. And then there was one more observational design that we talked about. Ecological designs, exactly. All right. So let's walk through each of these. So an ecological design, is the unit of analysis the individual or is it a group? A group. Ecological designs, everything is occurring in aggregate. So essentially we're comparing rates either across geographic regions, across groups, or across time. But the important thing is we have no information on individuals when we're doing an ecological. So I might compare the rates of mortality in car accidents before and after seatbelt laws. Or the rates of children with asthma for people who live close to highways and people who live in rural areas. But the important thing is that I don't know anything about these individual kids that live in these areas. I know the rate of childhood asthma in these regions and I'm comparing them. So it can be across region, it can be across time, it can be across groups, but it's always in the aggregate. What is the ecological fallacy?
Applying that to like individuals.
Yes. So taking the information that you learn from an ecological study and then assuming that that is true at the individual level. So we say, oh my goodness, the incidence of the rate of lung cancer is higher for people who live near highways than it is for people who live in rural areas. Obviously, the truck gas from the highways is causing people to get lung cancer. Not cool. Because at the individual level, that may not be true. What really is that everybody that smokes lives by the highway. Right? So you can't say an association that you see at the aggregate level is actually true at the individual level. Now, what is the purpose of an ecological study then? Why would we bother to do this if we can't make observations about individuals?
Would kind of help you form a hypothesis to do a more in-depth study at the individual level.
Absolutely. It's hypothesis generating. It gives us an idea. I mean, sometimes we just care are the rates of mortality from car accidents different in Illinois and Missouri. But sometimes we want to know why, and we say, okay, what's different between Illinois and Missouri? And we form a hypothesis, and then we can look at things on an individual level. All right, so that's the ecological design. That's the only study design we talked about where we're talking about aggregate. Everything else we talked about, we're talking about things at the individual level. So the case control design, or no, let's start with a cross-sectional design. So in a cross-sectional design, you go out, you sample a giant group of people, and you ask them, do you have this disease? Did you have this exposure? So you didn't know anything about any of these people to begin with. You just pulled together a group of people and you said, hey, are you sick? And did you have this particular exposure? Now that doesn't mean you didn't have a hypothesis at the beginning of the study. In a cross-sectional study, you usually have a hypothesis. I think that exposure X is associated with disease Y. And you could do your little statistical analysis and say, hey, yes, in this group, exposure X is associated with disease Y. What you cannot say is that exposure X causes disease Y. Why not?
You don't know the exposure came before.
Exactly. You don't know what happened first. You don't know if the exposure preceded the outcome. Lots of other causal reasons that we'll get to a little before, but that's the big one, is that in cross-sectional designs, you cannot establish a temporal relationship between the exposure and the outcome. All you can say is that in this group of people that we pulled, it looks like the more people that had the exposure, the more likely they were to have this disease. That's the extent of what you can say from a cross-sectional design. So a case control study. So a cross-sectional design, if we're talking about the period of time over which we have cross-sectional design occurs at one point in time. We're surveying. So what you might also hear it called is a prevalence study. Why might it be called a prevalence study?
You're looking at people that already had the disease.
You're looking at the people that have the disease at an existing point in time. You have no idea if these people are incident cases or if they've been sick for 20 years. I mean, it depends on the disease, I guess. If it's something that kills you tomorrow, then maybe. But, so we're looking at one point in time with a cross-sectional study. What are we doing with the case control study? Who do we start with? Who are we grabbing from the universe first?
People who have diseases of interest.
Yes. So we have people that are sick with a disease that we are interested in. And we identify those people. We put them in a little pot. Then what do we do?
Well, once you have the control, do you go backwards to see if they were exposed or not?
Yep, you skipped over the gathering controls part, but that's exactly right.
Yeah.
Yes, so we have the cases, and then we find controls. And where are we finding these controls? Yes, we ideally want the controls to come from the same source population as the cases. That doesn't always happen, but that is the preference, is for the controls to come from the same population as the cases. Why?
Because that helps you reduce confounders, because the population that they came from may have like similar, just have similar like characteristics.
It doesn't ensure that they have similar characteristics, but probably they have similar kind of types, but even more fundamental than that. So you're not wrong, but even more fundamental than looking at confounding. What do the controls tell us? Why do we care about them?
They give you base rate.
Yes, base rate. They tell us how many people would be sick, or I mean, how many people would be exposed. We're talking about the base rate of the exposure. How many people would be exposed if the exposure was not related to the outcome? So we've looked at, we get our cases, we get our controls, we look to see who was exposed. And if the exposure rate is the same in the cases and controls, then obviously that exposure is not influencing the outcome that we're interested in. It's not associated with it. If there are a whole bunch of more people in the cases that have that exposure than in the control condition, then we can say that the exposure is associated with our outcome of interest. What measure of association do we use when we're talking about case control studies?
It's RR, but I don't remember what it stands for.
It's the odds ratio, yeah. It's always something R. So the second one's always going to be R. Yes, so we talk about the odds ratio. Who wants to take a stab at what the odds ratio is telling us? Oh, you haven't talked yet.
It's the probability of having been exposed given that you have the
disease?
It's the odds of having the exposure given that you have the disease. But yes, so probability and odds are technically not the same thing. But it's the odds of exposure given that you have the disease. So because in a case control study we knew who had the disease, right? We started with the people that were sick. We know who's sick. Now we're just looking to see the odds of actually having that exposure we were interested in. So we're looking at an odds ratio, and I tell you that we're looking at the association between exposure X and disease Y. And we have an odds ratio of 2. We interpret that as,
Given you have disease,
Y.
why you are twice as likely to have been exposed?
Exactly, compared to people that don't have disease Y. Yes. So given that you have this disease we're interested in, you're 2 times more likely to have been exposed to exposure X than the people that didn't have the disease. Now, how do we calculate the odds ratio? What did I do with my chalk? Did anyone see where I put the chalk? There it is. All right. So again, in an odds ratio, we have a 2 by 2 table. And for all the 2 by 2 tables, we're going to put the disease status at the top. And we're going to put the exposure status in the rows. So this, for any measure of association for a study, we will always have disease at the top and exposure on the side. First thing to remember, because then formulas you have written down will always work if you set your table up this way. So we have, yes, you have the disease. No, you do not have the disease. Yes, you have the exposure. No, you do not have the exposure. And then we can label these A, B, C, and D. So, before I ask you about the odds ratio, what? Sorry? It's your review. We can always. I'd rather hear what you need to know.
No, I was just gonna say the formula for calculating it.
Oh, please do.
It's A divided by A plus C. Is it right? Now you're sticking me out in the place.
Sorry. We're talking about the odds ratio.
Yeah.
Odds are different. So in odds, it's the odds of exposure given that you have the disease, right? So we're going to start with this column.
Oh, okay.
So it's A divided by C. So A divided by C. Yeah, sorry. Over C divided by D. Which equals AD over BC, which is easier to remember. Although you don't have to memorize it, but if you rearrange your math cuts, that's what you're going to get. So that's easier to remember. And just remember it's the odds of exposure given that you have the disease. Which means within the diseased group, so within this column, what are your odds of exposure? So we're not talking about the odds ratio yet. What are the odds of being exposed if you're in the diseased column? It's A over C. That's right. Because odds, and this is the difference between odds and probability, odds is the number of successes divided by the number of failures. So here we're counting the number of people that had the disease that were exposed as success, and we're counting the number of people that had the disease that were not exposed as failure in our little experiment here. So the odds of exposure in the diseased group are A divided by C. The odds of exposure in the non-diseased group are B divided by D. So the ratio of those two odds is A divided by C over B divided by D, right? Odds in the diseased group, the ratio of them to the odds in the non-diseased group. Clear or awful? Or somewhere in between? Fair? Right. All right. So that's the case control study. Now we can talk about cohort studies. So in cohort studies, who are we starting with? Doesn't matter if we're doing prospective or retrospective, who are we starting with? We're starting with exposed people, right? Which means that everyone, at the start of our study, everyone is what? Disease-free. Or at least free of the disease that we're interested in. Or free of the outcome we're interested in. So in a cohort study, no one should be sick when you start. Very important. If we're doing a prospective cohort study, what does it mean if something is prospective?
Looking ahead.
We're looking ahead.
So like you have the initial data and then like going forward you ask them questions.
Right. So we recruit people today and we follow them through time. So hopefully we've recruited people that have the exposure we're interested in, and we recruit people that don't have the exposure we're interested in, and we follow them to see who gets sick. So when we're doing a cohort study, are we looking at incident cases or are we looking at prevalent cases? Incident cases, right? Because no one is sick at the start. So each person that gets sick is a new case of disease. So a prospective study, we gather everyone today, and we just keep following forward through time until our study ends. In a retrospective cohort study, everything has happened in real time, right? So we have data from 5 years ago. We go back and we say, hey, let's look at these data. Who was sick then? And we get rid of those people. And we still start with people that did not have the disease 5 years ago. And then, because we have this data existing in some database somehow or somewhere, we can then follow them forward through time, and we can still identify incident cases of disease. So it's retrospective because in real lifetime, all of these events have already happened. But as far as we're concerned in study world, we still started at the beginning and followed through time, right? Does everyone get the difference between the prospective and the retrospective? It doesn't matter which one it is. If it is a cohort study, you are starting with disease-free people, period. And you are identifying incident cases of disease. So if it says cohort, it means incident case, and it means everyone was disease-free at the start. Did everyone write that down? Very good. This is very important. This is the true distinction between the case control and the cohort study, right? And the cohort study is important because it allows us to do what?
Prove causality.
We can't prove temporality, yes. So we can't say they're causally related because we didn't experimentally manipulate anything. But what we can say is that we know for a fact that the exposure preceded the outcome. And temporality is the one and only thing you absolutely have to have in order to establish causality. Everything else, it's nice to have, it's nice to be able to establish that, but you cannot say something is causally related unless there's temporality, unless you can establish the temporal relationship. So what is the measure of association for a cohort study? What did you say?
I said relative risk.
Relative risk, yes. So, it's relative risk, or sometimes that's called the risk ratio. It's the same exact thing. You'll also hear of a rate ratio. Keep that in the back of your mind. A rate ratio is for when you have a dynamic cohort. So remember when we talked about dynamic cohorts, how people are moving in and out, we're calculating person time? It's kind of the same as the difference between cumulative incidence and incidence density or incidence rate. So we calculate a rate ratio when we're using incidence rate. We calculate the risk ratio, or the relative risk, when we're talking about cumulative incidence. So for the purposes of this class, the only thing we covered were fixed cohorts where we were calculating the risk ratio. So that's the only thing I expect you to be able to do. So we're calculating the relative risk. We have our cohort of people. We still set our 2x2 table up the same way. We have disease at the top. Yes, you have the disease. No, you don't. exposure on the side. Yes, you're exposed. No, you were not. But when we're calculating risk, what's our formula?
A over A plus C, and B over B plus D.
Use
No,
the
is it
rows.
A over A plus B
Yes.
over C over C plus D.
Exactly. So we have A over A plus B divided by C over C plus D. Why? Because if you can answer why, you won't ever mix it up again. Why is it calculated that way?
Because in the odds ratio, you're trying to improve, like, or you're trying to prove, like, the exposure. Here, we're looking at the disease.
Yes. Even more specifically, yeah, you were right. More specifically, we are talking about what's the risk of disease and the exposure. So we know everyone in here is exposed. How many people had the disease out of everyone that was exposed? So risk is simply the number of people that had the disease out of everyone in that denominator group. So we want the risk in the exposed. So the risk in the exposed is A over A plus B. And we're going to take the ratio of the risk in the exposed to the risk in the unexposed. So the risk in the unexposed is C over C plus D. And when we take the ratio of those two, we get the risk ratio. Now if I said that with the association between exposure X and disease Y, and you had a risk ratio of 2, now how are we going to interpret it when we're talking about a risk ratio?
Given that you have the exposure, you're twice as likely to get the disease.
Exactly. So now we can talk about it in the order that really makes sense, I think, fundamentally to all of us, right? The exposure is preceding the disease. Our study design has allowed us to demonstrate that the exposure preceded the disease. So now when we state our conclusions, we can state them as though the exposure is preceding the disease. So we can say that people that were exposed to exposure X are 2 times more likely to have disease Y compared to people who were not exposed to X. All right. Really quickly, let's talk about experimental study designs. I didn't ask you to do any statistical calculations or anything for the experimental study designs. We just briefly talked over them. Mainly because this isn't a clinical research class, this is an epidemiology class. So, experimental study designs, we talked about the fundamental thing that you need to know, right? So, investigator manipulation of the independent variable and random assignment to treatment groups. What is the difference between random assignment and random sampling?
Random sampling is when it's a true representation of the population versus, what was the other random one?
Random assignment.
Random assignment is just like you take whoever comes to you, but like they randomly assign to the control versus treatment group.
Exactly. Random sampling means I know everybody in the population, and the people that end up in my study are randomly picked from that population and ended up in my study, my sample. So my sample should be representative of the population at large. Random assignment, I take whoever walks in the door, but then I just randomly distribute them to the 2 groups. Now, why is random assignment important? What does random assignment do for us?
Takes out investigator bias.
Not always. That's a hope, but it doesn't always, but you're getting very close. So it has to do with bias, just not necessarily investigator bias.
It gives us a diverse study group.
I'm sorry?
It gives us a diverse or it gives us a diversity study group for the study.
I don't think I understand what I'm sorry. I'm missing something. An adverse for the study group?
Diverse.
Diverse. Okay, that would be why I didn't know what you were saying.
Yeah,
It doesn't necessarily ensure that they're diverse. It ensures what?
randomization.
the randomization ensures that the diversity is spread across them, right? Yeah. That the study group and the control group look alike in all the rest of the characteristics. So all those random characteristics, all the bizarre things that are associated with people, or all the things that possibly could influence the outcome, so long as they're randomly distributed, equally randomly distributed amongst the groups, they're not going to influence our outcome. We're still going to be able to detect association. It's not going to be due to some other factor. So the idea is that if we randomly assign people to groups, we're going to evenly distribute all those other characteristics, and now we don't have to worry about them anymore. So in the observational studies, when we're controlling for confounding, it's because we haven't been able to do that. But theoretically, and this is the bias thing, did you say bias? Yeah. The idea is that we're not going to be, the study's not going to be biased from these other little factors because we have evenly distributed them across the groups. And that's the importance of randomization. So we talked about a bunch of different types of study designs. So we talked about, I guess, the pre-test, post-test with random, with the randomly assigned control group. So a pre-test, post-test simply means you take people, they walk in the door, you randomly assign them to their groups, you give them a pre-test, you give the experimental group the intervention, and then you give both groups the post-test. So you use the pre-test to determine the baseline characteristics and to essentially ensure that your random assignment worked. You only give the intervention to the intervention group, and then you give everybody the same post-test, and you look to see if things changed, if the two groups are different. So with a pre-test, post-test, you can look to see if each group changed over time. You can also see if the intervention group is different from the control group. Why might we not want to do a pre-test? It sounds great. We should pre-test everybody so we know what happens at the start. Why might we not want to do a pre-test?
Like if you're doing exercise, it might spur some people to start exercising on their own.
Exactly. Sometimes doing a pre-test influences what people do after that. So if you have an exercise intervention and you ask people a bunch of pre-test questions about how much they exercise, and they're like, oh my gosh, I am a slug, I need to exercise more. And then you end up with a control group that exercises even though they were supposed to still be sitting in front of the TV. And when you do that, now it looks like your intervention didn't work, when in fact your intervention really did encourage people to exercise. The problem was that your pre-test also encouraged other people to exercise. So, in that case, you give a post-test only design. So people walk in the door, you randomly assign them to groups, you apply the intervention to the intervention group, and then you post-test. And so you can compare each group to each other, or the intervention group to the control group. And you're just essentially saying and accepting on blind faith that your random assignment worked the way that you intended. Now, if you're not sure that the pretest is going to influence people, you're a little worried it might, but you think that there's a possibility that within groups people are going to be changing across time and you want to still be able to do that, what is the study design we talked about that can look at both of those? It's essentially a combination of the two that we start following. The Solomon 4-group design. So the Solomon 4, seriously, I keep losing the talk. We have 2 treatment groups and 2 control groups. So we start off and we randomly assign to the 4 groups. So we have treatment 1, control 1, treatment 2, control 2. We only pretest this group. Treatment 1 and control 1 both get the pretest. We apply the intervention, oops, not to the control. We apply the intervention just to the treatment groups. And then we look at everyone at the end. So now we can look and see, hey, did our randomization work? And we can say, oh wait, the pretest, we can check and make sure the pretest didn't influence the outcome. And we have a bunch more data. Now why don't we just do this all the time? Because it takes a whole lot of people and it's really crazy expensive. The last thing that we talked about as far as experimental design, so the last one that's really important for you to know is the crossover design. So in a crossover design, people get to serve as their own controls, and you have two groups, right? So you have group 1 and group 2. So let's say we're comparing drug A and drug B. So we start off and group 1 is getting drug A, and group 2 is getting drug B. And we pre-tested them before and looked to see where they were at baseline. Group 1 gets drug A, group 2 gets drug B. Now we look at them again, and we make sure these drugs are out of the system, and we switch. Now group 1 is getting drug A, and group 2 is getting, or group 1 is getting drug B, and group 2 is getting drug A. This design lets us make comparisons between groups when they're on the same drug. It also lets us see within people they get to act as their own control. So if we think that drug A works better, we'll be able to see that when group 1 was on drug A, they were doing better than group 2. And when group 2 was on drug A, they were doing better than group 1. We can also see that within group 1, they did better than when they were on drug B, right? So we can look at all of that together. This is kind of the foundation of a lot of drug trials. Now, the study designs we've covered in here are not completely, totally, end-all, be-all study designs. These are the foundational designs that you need to know before you can learn the other ones. All right. So, most important things to cover after that, as far as at least the stuff you guys gave me. Let's talk about confounding and effect modification. Let's see. What is confounding? Anyone, just shout it out. What's confounding?
Something unexplainably, something other than what we're testing for can cause the outcome.
Yeah, not necessarily causes it, but if we,
It's strongly associated with it.
yes, so, yeah.
I would say it's something that we don't plan on being in there, so we don't control it.
Yeah, well, hopefully we do control it, but yeah, the idea is basically that when you have this association that you're expecting to see between two variables, right? And we were like, yay, this association's there, and then you're like, uh-oh. It's really because of this third variable over here. That third variable is the compounder. So we talked about the association between coffee drinking and, between alcohol use and lung cancer. And there's a big association, a strong association between using alcohol and lung cancer. But oops, it's because all the people that use alcohol smoke. So really the association between smoking and lung cancer, it just unfortunately also happens that smoking is associated with alcohol use. So remember the criteria we talked about? A compounder has to be associated with the outcome, it has to be associated with the exposure, and it shouldn't be in the causal pathway. However, that's third one is slightly fudgeable given the situation.
Can you repeat the third one?
Yeah, so it can't be in the causal pathway. So we can't say that Lipitor is a confounder in the association between high cholesterol and myocardial infarction, because Lipitor causes your blood pressure, your cholesterol to go down. So it's the reason for. Yeah. But the big ones your confounder needs to be associated with the outcome, and it needs to be associated with the exposure independently. So we know smoking is associated with alcohol use. People like to drink and smoke at the same time. And we know that smoking is associated with lung cancer. Right? Now what's effect modification? So confounding is bad. Confounding is a bias. We don't like it. What's effect modification?
So there's different, you guys are between different strata.
Yeah, so essentially it's when, based on the level of the third variable, the association between the exposure and the outcome changes. So, for example, you have a drug to treat diabetes, but it only works in people that are over the age of 65. So age is an effect modifier in that relationship, because the relationship, like drug X, doesn't work at all in helping control diabetes for people under 65, but it's really effective in people over 65. So based on the level of your third variable, the relationship between your exposure and outcome is different. So these are two very different concepts. Effect modification is something, yay, we like to see it because it tells us something. Effect modification tells us how we can target interventions. It's how the exposure and the outcome are differentially related depending on whatever variable is. Confounding is just a bias. Confounding it means that it's hiding the true answer. Where the confusion sets in is that we assess them using the same method. Right? We use a stratified analysis to look at both effect modification and confounding. And that's, I think, where things get cloudy. Because they're two completely separate concepts. So let's walk through a fun confounding example. So we've done a case control study. And we're investigating the effects of chemical X exposure on having a heart attack. And we look at our full sample. We have our cases and our controls. And we have the people that were exposed to chemical X and the people that were not exposed to chemical X. Alright, and this is what we find. So, what is the first thing we need to do? We're doing a case control study. We want to know about the relationship between chemical X and having a heart attack. The first thing we do. Yeah.
Calculate odds ratio?
Yes, we calculate our odds ratio. Now, what kind of odds ratio is this? What would we call this? This is our crude odds ratio. It's the one that is actually what the numbers are telling us. We haven't done anything to it. We're going to calculate the crude odds ratio. So we calculate that how?
AD over BC.
AD over BC. Excellent.
Thank you.
So 176 times 147 over 1 over 3, 103 times 74. And we get a crude odds ratio of 1.76. Alright. So this is saying that people have a heart attack are 1.76 times more likely to have been exposed to chemical X compared to people that didn't have a heart attack, right? But let's just say, for argument's sake, we were a little worried that gender might be doing something funny here. We were worried that gender might be confounding this relationship. That maybe it's just gender that's explaining the heart attacks and not chemical X. So the next thing we do is what? We stratify based on gender, right? You can't do this with this information. I have to give it to you because you have to know their variables. So let's say we get these results. So we have for men, we have and for women, alright, so we end up finding that for men, now we can calculate the stratum-specific odds ratio. So stratum-specifically just means, so the stratum for the OR for men is, in this case, what is it? 4.97. And for women, 2.40.
Shouldn't those numbers add up to the crude?
Did I? There should be the total. No, they shouldn't add up to the crude. But you mean the odds ratios?
For the stratum, yeah.
Well, we've taken those. Does it not add up? It should be the same, the right number. Did I not do this right? Sorry, there were like people kept calling me and interrupting me. How many people are in here? 249.
That's okay, we get to it.
Okay, theoretically the numbers should add up, and if you total all of these, it should be the same total in there. This is what happens when people keep calling you while you're trying to write. It was none of your fault, but people kept calling me with problems, and then I got distracted. So yeah. Anyway, let's just pretend that that adds up, and that this is the answer that you get. Right? So let's just ignore these. Pretend I just gave you these answers. Okay? There you go. So we stratified them and we got this. So we got the odds ratio in men was 4.97, the odds ratio in women was 2.40. Here's where things get dicey. This is when we have to decide whether or not we're really assessing for confounding or if we're assessing for effect modification. Right? At this point. So we started with our full thing, we stratified them. We got the stratified measure of association. And now we have to look at those. Do those numbers look the same to you? No, they're not even roughly the same. Those numbers are very, very different from each other. Which means what? It means that the relationship between our exposure and our outcome is a whole lot stronger in men than it is in women. So since it's a whole lot stronger in men than it is in women, we're going to say, uh-oh, we thought it was confounding, but maybe it's not. Maybe the relationship between chemical X and having a heart attack changes depending on whether or not we're looking at men and women. Which is the definition of what? Effect modification. So, step 1, you calculate your crude measure of association. Step 2, you stratify and you calculate your stratum-specific measures of association. You compare the stratum-specific to each other. If those numbers are different from each other, like by more than 25%-ish. If they are different from each other, you say, uh-oh, it's probably effect modification. I should stop here, and I should just talk about these two groups separately. I will report the results separately, because there's something different going on in men than there is in women. Now let's say that instead of stratum-specific men 4.97 and women being 2.40, we stratify them and instead we get that the stratum-specific odds ratio for men is 2.38. So we stratified and we say, hey, in men the relationship looks like 2.38, and in women the relationship looks like 2.4. Are those numbers different from each other? Not really. And since the stratum-specific estimates are not different from each other, we know it is not effect modification. Because for it to be effect modification, the stratum-specific estimates have to be different from each other. But since in this example, now they're not different from each other, now they're the same, we say, okay, it's not effect modification. So what do we want to do next? What are we going to compare them to next? The crude, right? So we have this first, this is where we started. Our starting point and our end point. So now we can say if you were to calculate the adjusted odds ratio, which I'm not going to ask you to do on the exam, so don't worry about it. But if you were to calculate the adjusted odds ratio, you'd get an adjusted odds ratio of about 2.39, right? Because if you're right in the middle of those, it'd be the same. Now, is the 2.39 different from the crude? Now that we have controlled for gender, we have controlled for variability based on gender, do we come up with a different answer? Yes, we come up with a very different answer. That is confounding. So it doesn't have to make the relationship disappear, it has to change the relationship. So I think a lot of the examples we give, the relationship kind of like completely disappears, and so that can happen, that's confounding. But it's also confounding if you get a different answer at the end. So what you want to see is if at the end of the game, if this answer is different from your crude answer, and if it's different by more than about 10%, you say it was a confounder. We're seeing a different relationship between the exposure and the association now that we've controlled for that third variable. Right, you had a question.
So if they're close to each other and close to the crude, that means we don't have effect modification or confounding.
Exactly. Exactly. So if they're close to each other and they're the same as the crude, you say, that variable obviously doesn't make any difference. Exactly. Yeah.
So what if one's way smaller and then one's significantly larger?
Then it would be, what do you mean, from the crude or from each other?
So like, let's say one of them is smaller than the crude and then one's like...
Then it's effect modification. So there are times, so what happens, there's a couple of ways. I think effect modification is actually easier to look at when you graph it, so I probably should have done that in the first place. But what happens is, so you'll look at men, and you'll look at women, and you can't even read that. But so you can say, okay, so we have the crude, and when we stratify it, they both go like that. Or you end up with a relationship that goes like that. Sometimes you end up with one that's now a protective effect, and the other one is a much higher risk factor. So long as they're different from each other, it does not matter in which direction. All right. Any other questions about confounding and effect modification? I know that's not the easiest topic to get through. All right. The one other thing that was really, really big that everybody kept talking about was the difference between necessary and sufficient causes. In all honesty, I'm at a loss how to explain this better. I have tried, but we'll walk through it again and see if we can all come to a better understanding of necessary and sufficient causes. But for a cause to be necessary, so let's say A is a necessary cause. For B to happen, A has to happen. So,
in order to get rabies, you have to have been infected with the rabies virus. The rabies virus is a necessary cause of rabies. You will not get rabies unless you've been exposed to the rabies virus, right? So if something is necessary, it means the outcome cannot happen unless that exposure happens. So I think necessary is usually an okay thing to understand, right? It's sufficient that becomes the problem. Because sufficient simply means that that thing alone can cause the outcome. It doesn't mean it's the only thing that can cause the outcome. So, let's see, let me find a good sufficient example. So, getting a C+ in this class is sufficient to pass, right? You pass the class if you get a C+. Now you don't have to get a C+ to pass the class. You could get an A, right? So it's not necessarily necessary that you get a C+, but it's sufficient. C+ will give you a passing grade. Let me trying to find health examples, and the problem is there's very few sufficient ones. Oh, here's a good one. So, being able to run a 4-minute mile is sufficient evidence that you are physically fit. People that are not physically fit cannot run a 4-minute mile. Now, it's not necessary to running 4-minute mile to be a physically fit individual, right? But it is sufficient to prove that you're physically fit. Yes?
Can you restate the sufficient definition again?
So sufficient simply means that that thing alone is enough to ensure the outcome.
So like the presence of a sufficient cause will automatically cause like the outcome, but the absence of necessary one means it can't.
That's exactly right. Exactly right. Yes. So the presence of a sufficient cause, if a cause is sufficient, it will produce the outcome. But it doesn't mean it's the only thing that can produce the outcome. It just means it can. A necessary cause means it has to be there or you will not get the outcome. So if the necessary cause is not there, there will be no outcome. It will not happen. So there are things that we consider both sufficient and necessary, right? But there are things that are just sufficient, and there are things that are just necessary. But you might need some other factors to influence. Yeah?
So like the Ebola virus is sufficient and necessary to get Ebola?
Yes. Yes.
But HIV, so and then...
Well, here's the problem with like the sufficient and necessary, is that in the broadest sense of the term, yes, you would consider Ebola both sufficient and necessary. But when you look back and say, okay, well, not everyone that's exposed to Ebola necessarily gets Ebola. There's got probably some other thing in there that's influencing it, so maybe they didn't get enough Ebola. So maybe it's like you have to have a certain dose of Ebola, and that is sufficient and necessary. Does that make sense? So when you start talking about environmental influences, it gets messy. And quite honestly, I don't think I even want to teach sufficient and necessary causes anymore because it's just a whole bowl of confusion. And it's one of those things. The problem is that very few things in this world fit neatly into those categories. What it really is there's component causes. So there may be sufficient causes. Sufficient causes exist. But when we're talking, and necessary causes exist, but what really gets most diseases involves some combination of causes in order to manifest, right? So, lung cancer, smoking is not a necessary cause of lung cancer. Some people might consider it a sufficient cause of lung cancer, but if it was a sufficient cause of lung cancer, then probably everybody that smoked could get lung cancer. So there's obviously other component causes, which is why the necessary and sufficient really is talked about a lot more in the infectious disease world, because when we're talking about chronic diseases, very rarely are chronic diseases ever that simple. So when we're talking about causal mechanisms of chronic diseases, that's when we get to the nice, fun temporality analogy, like the whole Bradford Hill criteria. Right? So there are a couple of necessary and sufficient causal thingies on your exam, but they're small, and I think that they're obvious enough to where, and if everybody misses one, I'll just give you all credit for it. How's that sound? If over 50% of the class misses a question, I usually just toss it anyway. Very rarely does that happen, but if that happens, then obviously it was a bad question. I think I've vetted most of them, but let's see. So the Bradford Hill criteria I think we should touch on, and then I will open it up to whatever else you guys would like to talk about. Where did I leave my... All right. So everyone knows what I'm referring to when I'm talking about the Bradford Hill criteria, right? Or just the Hill criteria. Sometimes it's called both, but you guys all at least have a general understanding of that, right? And we talked about earlier that temporality is the only one of those that you have to have. You cannot violate temporality and conclude that X causes Y. Because your cause has to precede the effect. That's logic, right? All of the other ones, the more you can establish, the more of these criteria that you can establish, the better your case for a causal association. Right? So we have the strength of the association.
the stronger your odds ratio or risk ratio, the larger it is, the more likely that there's a true association there, and that it's not due to something like confounding or other bias. It doesn't mean it can't be, but the stronger your association, the more likely it is that there really is a true association there. So if you have a strong association, that's support for causality. It doesn't mean that there is causality, because you can have weak associations that are causally related. Or you can have strong associations that are completely due to something else. Dose response makes more sense when we're talking about kind of pharmaceutical, biological mechanisms than if we're talking about kind of social interventions. But general dose response, if you can demonstrate that the more of the exposure you've had, the more likely you are to get the outcome, that's really solid evidence for kind of inferring causality. You can show that smoking a pack a day for 10 years means you're more likely to get lung cancer than if you smoked half a pack a day for 3 years, right? That's dose response. Or even half a pack a day for 10 years. Let's keep it consistent. Consistency. All these different people have done studies, and they all came up with the same idea. They all got the same response, especially if you have different study designs. Because different study designs, like we talked about earlier, have different biases. Different study designs are more or less susceptible to certain types of bias. So if you can show that you're getting the same result regardless of what study design you're using, or that lots of investigators that have done things slightly different way are all getting consistent results, that's more support for a causal association. Now, not seeing consistent results doesn't mean that there's not a causal relationship. Sometimes people define things differently, or they use different doses, right? But if you can demonstrate consistency across studies, you have more support for causality. Biologic plausibility. You essentially have some theoretical reason for thinking that what happened should happen, right? Based on what we know in science, this seems like a reasonable association. It seems like reasonable to believe that would cause the other thing. That's kind of a weak one, because our theories can be wrong, but reversibility. If you remove the exposure, the risk of disease goes away, and the risk of the outcome goes away. Or you can take it back. Now, reversibility is kind of hard to demonstrate, because sometimes once you've had the exposure, that's it. You can't take it back, right? So if I'm giving you cognitive behavioral therapy, I can't make you unlearn the skills that I taught you, right? So reversibility is hard to demonstrate. But when we were talking about the drug trials with the crossover study, when you have people and you say, okay, I gave you this drug and your eczema got better. I took it away, your eczema got worse. I gave it back to you again and your eczema got better. You can show that, demonstrate that relationship. You have a stronger case that the drug I gave you is actually improving your eczema, right? And then study design, obviously we talked about the different study designs earlier, and the different ones are more or less susceptible to certain kinds of biases. The main biases that we talked about were selection bias and information bias. Now, bias is simply a systematic error, right? So it's not random error that's distributed, because that's just kind of noise and it happens. It's when you systematically have something that's making you see something that deviates from the truth. So when we talk about selection bias, that's when there's systematic differences between those who are selected for the study and those who are not. Especially when it's systematic differences between the cases and the controls, or between the exposed and unexposed. So if there's some systematic difference between the people that were the cases in our study and the people that were controls, so we pulled all of our cases from the ER, and we pulled all of our controls from whoever was randomly home in the neighborhood when we knocked on the door, it's possible those two groups are not the same. And when we talked about earlier, we wanted our controls to be from the same source population as our cases, right? So when that doesn't happen, we're talking about having a selection bias. And then we talked about Bergson's bias. So that's just when, Bergson's bias is simply when you're in the hospital and you're using hospitalization rates. When the hospitalization rates are different for like your group compared to whatever control group that you're using. Information bias. So selection bias occurs when people are entering the study. That's when people are coming in the door, generally speaking. Information bias occurs after people have gotten into your study. Now that they're answering things, information bias. So information bias just means that there's something wrong with the way that you're measuring the exposure or the outcome. So that could mean, and when we have information bias, that can result in misclassification. So misclassification simply means you put people in the wrong bucket. You took people that were actually cases and you accidentally put them in the control bucket. Or you took people that were controls and you accidentally put them in the case bucket. Now in any study you're going to accidentally misclassify a few people. So long as there's no systematic rhyme or reason to how people get misclassified, so long as the misclassification is actually kind of randomly distributed amongst the groups, it won't hurt your study. Now, if that's called non-differential misclassification. It's kind of just whatever. Differential misclassification means that there is some systematic thing that's causing you to accidentally misclassify a certain group of people. And that's when you have a problem. Because when your misclassification is differential, if it's different between the cases and the controls, if you're more likely to misclassify cases than you are controls, that's going to cause a problem. That's going to lead you to the wrong conclusion. Now, non-differential misclassification can be due to lots of things. Some of these are these other things of bias, these other types of bias that we talked about. So recall bias. What's recall bias? Anyone guess?
People who had an outcome, they're more likely to remember all the
Exactly.
associated with it.
Exactly. People that have a particular outcome are more likely to remember the exposure than people that didn't have the outcome. Or essentially, there's differential recall between your exposed and unexposed, between your cases and controls. Reporting bias. It simply happens when a group of either cases or controls don't report the exposure, either due to social reasons or due to laziness, I don't know. But it's when a larger percentage of either your cases or controls systematically report the wrong thing. Wrong answer. Sometimes reporting bias gets called social desirability bias because it happens frequently when you're talking about sensitive topics like drug use, sexual behaviors, things like that, things that people are kind of embarrassed about. A lot of times they're not willing to admit they had a particular exposure because they think it's not socially desirable to have done that. Surveillance bias happens when you have essentially a better count of a more accurate count of the people that have the disease in a population that's closely monitored. So it looks like airline pilots are more likely to have, I don't know, blindness. I'm making this up. But that's because airline pilots get screened for blindness every single year, and the general population doesn't, right? So it's not that truly in reality they have a different rate of disease. It's just that we find it more often because we're actively looking for it in that group. That's surveillance bias. And then we talked about confounding. All right. Those are the big things I wanted to cover based on what you guys sent to me in your little letting us point things. Anything I didn't cover that you guys want to talk about? Now is the time to ask, because once it gets 5 o'clock, your midterm will be posted and I will no longer answer any questions. Well, I'll answer clarification questions, but I won't answer any topical ones.
What's the
It is due next Wednesday on the 12th by 5 p.m. You do not have to come to class. Do not show up here. I will not be here. I will probably still be sitting in jury duty.
Oh.
Do you have jury duty?
Yeah, starting Monday, but they said to like hold 3 days just in case. So the last time I had jury duty, I was there for maybe 5 hours. So I'm hoping that we will have a repeat of that situation. But with my luck, I'll probably get picked for some jury that'll last a year or something. Did you have, yeah?
Is it timed?
I'm sorry?
Is it timed?
No. So in the week 15 folder under the lecture hall blackboard, there are 2 documents. One is your final exam, and one is an extra credit assignment. Both are due next Wednesday by 5 p.m. There's a place in the assignments folder to upload them just like every other assignment. Do not turn it in late. I get very peeved because I seriously have 2 days to turn these things around to get grades in on time. I have lots and lots of stuff to do with. So, I need you to make sure you turn it in on time. If you don't turn it on time, I start counting off points. 5 points for every hour. Yes?
Is this like the first method of multiple choice to hold a few essays or all essays?
There are, I think, like 29 multiple choice, some short answers, and then some essays. It's a rather long exam.
So like the first one then?
It's a lot longer than the first one. There are some multiple choice questions at the beginning of the exam, and then there's a lot of short answer and essay stuff. But you guys are free to use your notes, to use your books. Do not talk to each other, that's the rule. So no conversations, but you are free to use your own, anything that you've written down or whatever, all of that is fair game. Yeah?
You'll open that up right after.
It's already set to open. Set it to open, it will open at 5. It is there. If you have any questions about clarification issues, email me. All the topic stuff, you guys have 45 more minutes to ask me. So, anything else? The extra credit is worth a bonus 10 points on the exam. Do it the same time. Yeah.
How would you do with the confounder? Like, so if you had a confounder, confounding variable, would you just by separating the probably would you like stratifying the care?
If you have a confounding, if you identify something as a confounding variable, you report the adjusted odds ratio instead of the proved.
Okay.
So you talk about it, and then you just report it as you have to tell that you adjusted for that particular confounder. So you say after adjustment for blank, here was the relationship. Anything else? Thanks for an awesome semester.